All right, so our last section we have here is LC circuits, which, as the name implies, uses both an inductor and a capacitor. So to motivate how this will behave, remember that capacitors and inductors have opposite behaviors at long times. Capacitors behave like gaps, inductors behave like wires. So these two circuit components are going to be locked in this constant competition to store energy in their respective field. Usually it begins with a charged capacitor, and you can imagine if we close the switch, charge will begin to flow because this acts sort of like a battery, but the fact that we have charge flowing is going to generate a magnetic field through the inductor coils, and that stores energy. So we see there's sort of this trading back and forth happening. And the reason we didn't include a resistor is because if we include a resistor, there will be some energy dissipated through this process. So we'll see this is an example of energy oscillation, where it might begin in the electric field, goes to the magnetic field, goes to the electric field, back and forth and back and forth. So we're going to start just with a pretty basic model of the LC circuit, then we'll get into the math. So at each of the times, we're really going to draw everything. We're going to draw the charges on the plates, we're going to draw the E field, we're going to draw the current, we're going to draw the B field, all of those things. So let's start. Initial state of the circuit, t equals 0. So we're going to say that we begin with a charged capacitor, because that's the easier of the two cases to actually come up with. It's usually a bit more contrived to begin with the current in the circuit case. You have to have one of those two-state switches for that. All right, so if we have a charged capacitor, that means that there's energy stored in this electric field. And initially, we've just closed the switch, so there's no current yet. So that means that there's no current in the circuit. So there will be no magnetic field in the inductor. So we can say at this point, all of my energy eggs have been placed in the electric field, and none of it has been placed in the magnetic field. But of course, it's not going to stay this way forever, because a quarter of a cycle later, what's going to happen is the capacitor will become fully discharged, right? If we let this capacitor go, we know that charges are going to move, conventional current is going to flow counterclockwise, and that's going to be an energy stored in the magnetic field. So here, at this moment in time, we have 0 charge on the capacitor plate, because all of that charge has discharged and is moving around the circuit counterclockwise. And as a result, we're going to have a magnetic field around this inductor. So at this time, none of the energy is in the electric field because the entirety of the energy is in the magnetic field. And again, we're saying there's no losses because there's no resistance. All right, what about a short time later? Well, we have current kind of flowing this way on the circuit. So what's that going to do? That's going to charge up the capacitor. Except this time, the charges are going to flip because the positives are heading towards that bottom plate this time. So we get a reverse in polarity. Now that still means that the current is 0 because we're at maximum charge. Because if we weren't at 0 current, the capacitor would still be charging. So once again, even though the field reversed direction, we can still say that all of our energy is going to be in the electric field, and none of it's in the magnetic field. Then another quarter cycle later, this capacitor is fully charged, so it's going to flip the current, because now it's going to discharge, but that current is going to go this way now as we discharge. So we have, instead of a counterclockwise current, this time we have a clockwise current. So that means our B field through the inductor is going to exist once more, and it might look something like this. And if it's maximum current, we're fully discharged. So this means we have none of our energy in the electric field and all of it in the magnetic field. So what is that doing? Well, we see that that's going to charge the capacitor with the top plate becoming positively charged. And oh, look, we're exactly back to where we started. With no current because we're fully charged, meaning all of our energy is back in the electric field. Make the bars a bit larger. And there's no energy in the magnetic field. So we see that there's a little sort of trading happening, just like we thought. So it starts all in the electric field, then the capacitor discharges. So since it's discharging, there's current, which creates a magnetic field. But that current charges the capacitor back up, so there's energy in the E field again. Then the capacitor discharges again, sending current through the inductor again. So there's energy in the B field. But that current then charges up the capacitor, and we see what's going to happen. And since there's no resistance, this will happen forever in a cycle. So let's graph qualitatively what's happening. So first, our capacitor was all the way charged. Then our capacitor was all the way discharged. Then that current was going around the circuit to charge the plates the opposite way. Then the capacitor discharged again, but that current caused the polarity to flip again. So we can probably guess what we're going to get based on this shape, right? It's going to wave, so it's going to go like this. So we can definitely guess what trig function this is, right? We see it's oscillating. What about the current? We're saying clockwise is positive. Well, for the current, initially, as soon as we flip the switch, nothing. Then we had a counterclockwise current to begin, which we're saying is negative. Then the capacitor charged up again, so there was no current in the circuit. Then the capacitor fully discharged the opposite way. And then the capacitor charged once more, so we see much better. Oh, this was a much better graph. We see we get a different type of wave. You can probably guess what relationship we'll be fishing for because we have current and charge. That's definitely a calculus relationship. Yeah, here we go. Are our two graphs consistent with each other? Well, of course, the fact that you're seeing this recording means that I did it right and didn't have to reshoot anything. So we know it's consistent. All right, great. Why? Well, remember that we have a relationship that says I is equal to dq dt. And what is that on a graph? That's the slope. So let's check. We see I start with 0 slope. Then I have maximum positive slope, 0, maximum negative slope, 0, and then maximum positive slope, and 0 again. So if this is right, our current graph should look like 0, negative max, 0, positive max, 0. So let's check that out. 0, negative max, 0, positive max, 0. That's exactly consistent. So we see that I is the slope of Q as expected. So we got to throw in an as expected, of course, right? Using our graphs, determine expressions for Q and I. Okay, so we know their trig functions, and we also know their amplitude. So let's begin with Q. Q is equal to Q max. Then we have to pick what trig function to use. Well, look at the graph of Q. The graph of Q is maximized at the start. So the trig function that's maximum at the start would be cosine. And we know it's going to have some sort of angular frequency omega. But also, omega wasn't a variable we got. Instead, we have the period. So there's this relationship that omega is the rate that you're sweeping out angle. So omega is defined as the amount of radians you sweep out per second. So you could sweep out 2 pi radians, a full circle, in 1 period, capital T. And that is a formula sheet equation, by the way. So this would tell us that Q max is equal to cosine of 2 pi over capital T times lowercase t. All right, what about I of t? Well, we also can figure out I of t pretty easily. We know its maximum current was I max, and if we look at this graph, it's actually 0 at 0. So that's not cosine, that's sine. And also see that this graph actually begins going down, and that's not what sine of x does, that's what negative sine of x does. So this is negative I max times sine, and the period is, of course, the same. So these are our two expressions we have. Then we lastly want to verify this relationship between I max and Q max. Well, we see these are both the amplitudes, and I can get from Q to I via differentiation. So I should probably use the fact that I is equal to dq dt to do this. So what is dq dt? Well, Q, we said, is Q max times cosine of omega t, where omega is 2 pi over the period. And now we're just going to do some calculus. So Q max, of course, is not involved. Derivative of cosine is negative sine. So we can already see something worked out in our favor. And then we have to use the chain rule, right? Derivative of the inside would be just the constant omega, 2 pi over t. So we see that I of t can be rewritten as negative Q max times omega times sine of omega t. And that's proving the claim. That's proving the claim that we wanted, because we see that our amplitude in front is going to be I max. So we can conclude that I max is equal to Q max times 2 pi over the period. And again, all we did is we just set their amplitudes equal, right? We know that I max is the number in front of the sine curve. So using our differentiation, we figured out an alternate way of finding the amplitude. All right, we got things changing. We got things oscillating. So of course, we have a differential equation to model it. And this is different because it's actually second order. So this is a differential equation that doesn't relate Q and its derivative. It actually relates the charge Q to its second time derivative. So if we wanted to come up with this, you could use conservation of energy, or you could use just a loop rule idea. So we could set up a loop equation. If we set up our sum of our delta V's, we could say that just to help us with the signs, we'll use our phantom battery trick. We'd gain some volts across the battery, we'd drop some volts across the inductor, we'd drop some volts across the capacitor, and we're back to where we started. But we have expressions for each of these things. The voltage drop across an inductor is L di dt. We have no battery voltage, so we don't have to consider that. And the voltage drop across a capacitor is Q over C. Then we can bring one of those terms the other side, and we would get L di dt is equal to negative 1 over C times Q. But remember that current is the derivative of charge. So if I have the derivative of the charge with respect to time, that's a second charge derivative. And moving L over, I get the desired result of d squared q dt squared equals negative 1 over LC times Q. So we do actually get that differential equation from the loop rule. Again, I just use this rather dubious trick of pretending that there's a battery. but you will always get the signs correct if you start with a battery term and just remove it if there isn't one. It also works, of course, if there is a battery, you get you get more interesting solutions if you allow this situation to be forced. So as per usual, this is a differential equation, so we'd love to have satisfying ways to do it, but we just guess. So we are saying a function is equal to itself, a function's derivative, its second derivative is equal to a negative constant times itself. So here's where we run into an issue. Because if you think the solution is like e to the t over tau or something like that, it doesn't work. Because even if there's a negative, you'd be multiplying by the chain rule factor twice, so it removes the negative. So this means the solution actually isn't an exponential. I'll put a little asterisk there. It can be an exponential if you know a certain number that squares to -1 and use some Euler identity fun stuff. But if we look at this for a while, we see that that's actually not e. It looks like a trig function, right? Because if we have sine, the derivative of sine is cosine. The derivative of cosine is negative sine, and so on. So we see it's this cycle where if you take two derivatives, you're back to where you started with a negative sign. And that means this factor comes from the chain rule. So by knowing that, we can construct the following solution. We know that the chain rule factor that's multiplied by itself to get to the second derivative must be something that multiplies by itself to get 1 over LC. So this tells us that 1 divided by square root LC is this quantity omega that goes inside the trig function. And it's okay if that's a bit weird for you. We can take this as sort of a just fact. This comes from differential equations. Now, if you remembered simple harmonic motion and studied that in a mechanics course, this is that same omega that tells you the oscillation angular frequency, but we're not assuming you've encountered that before, and we're trying to motivate it by saying two derivatives is proportional to itself times a negative. It's got to be a trig function. So this number must be the angular frequency squared, because you had to chain rule twice because there were two derivatives. So this is a formula sheet expression, so we actually never have to derive this for ourselves. This is the characteristic frequency of an LC oscillator. It's the angular frequency, but it's telling you how rapidly things are oscillating, up to a factor of 2 pi at least. And we're going to look at the cases where you're beginning with either a fully charged capacitor or a fully uncharged capacitor. So no phase shifting or anything. We're just looking at the fact that your capacitor is either fully charged, so you want cosine, or your capacitor is fully discharged, so you want no charge, so you want sine. Because cosine 0 is 1, but sine 0 is 0. So now we can use our relationship from earlier that we said omega defines the rate that you sweep out angle. Well, we know that this is constant in this motion because the frequency is the same. So you sweep out 2 pi radians in however long it takes you to complete one cycle. So this means that we can solve for t, because we can get omega t is equal to 2 pi. So this means capital T is 2 pi over omega. But omega was defined to us as 1 divided by square root LC. So we get 2 pi divided by 1 divided by square root LC. So we get a double denominator, which we can always swing up to the top to get a numerator. So this is how you define the period. So the bigger your inductance or capacitance, the longer it takes for a cycle to complete. All right, we'll begin with these LC circuits below. All the capacitances are the same and all the inductances are the same. So what we're going to want to compare is the frequency, so how long it takes for each cycle, and then the period. Sorry, the frequency is how many cycles per second you have, and the period is how long it takes for each cycle. So maybe it might help to write that. This is cycles per second. And the oscillation period is seconds per cycle. So we can actually kind of see the little thing that's going to happen with these rankings. So first of all, we know that the frequency lowercase f is the cycles per time. And we also know that omega is defined as 2 pi times f. And why is that? Well, if f is how many cycles you're doing per second, if I multiply 2 pi by the amount of cycles per second, I'm getting radians per second. So that's kind of some motivation there. So we see that this means, reasonably so, that frequency and angular frequency are proportional. One is just about cycles, one is about radians. So first we want to rank omega, which is 1 over square root of LC. And then we see the other ranking is really easy, because if we ranked number of cycles you do per second, and then we want to rank the number of seconds it takes per cycle, well, those two are inversely related. We also have the relationship that says period is 1 over frequency. So this would be the reverse ranking. So that means let's work out our omega values for each of these. All right, circuit 1. Well, you're just a capacitance C. So our omega here would be 1 over square root LC. So maybe let's just call this, we can call this 1. Circuit 2. Well, we have two capacitances in series. Remember, series capacitance follows the reciprocal rule, so this is actually C over 2. So this omega would be 1 over square root of L times C over 2, which would be 1 over the square root of 1/2 if we're using our proportionality. So that square root 2 in the denominator would come up to the numerator. So this is square root 2 in relation to the first one. And then circuit 3, well, we see that we have two capacitors in parallel. Those are add with the addition, just standard addition. So omega for this one is 1 over square root of L times 2C. So the 2 remains in the square root and on the bottom in this one. So this one would remain as 1 divided by square root 2. So we see our 3 frequencies we obtained were 1 over root 2, and 1. So if we're ranking them, the lowest frequency would be, that would be case 3. Then we have 1, and then we have 2. Because we said that this angular frequency was 1 divided by root 2. This frequency was 1, and this frequency was square root 2. And it makes sense because the one with the largest capacitance, should take the longest to complete a cycle. And now we just do the opposite, because period has the opposite relationship. So we just do 1 over t's. So if we did 1 over f for each of these, u would be square root 1 over square root 2. U would still be 1, and then u would now be square root 2. So we see there's some flip-flopping because these are reciprocals of each other. So this 1 over root 2 becomes a root 2 over here, and so on. Now, there's a lot of scary things happening with trig functions, but at the end of the day, we're going to solve most LC problems using energy. So there's 3 ways that we can write total energy in an LC circuit. All of these are equivalent. So at any random time, we could say the energy is given by Q squared over 2C, the capacitor's electric field energy, plus 1/2 Li squared, the inductor's magnetic field stored energy. Or we could say U total is the maximum amount of energy stored in the capacitor, or it's the maximum amount of energy stored in the inductor. So if you know some extremes, it's actually really easy to get that. So let's justify why all of these give the same energy. So first, we know that U total can be written as the electric field stored energy plus the magnetic field stored energy. So since we're usually given the charge and capacitance, we probably want to write this as Q squared over 2C. And then we only have 1/2 Li squared for this. All right, so that's kind of just that's our starting point. So we could also say that the total energy is equal to, which one do we do first? Q. We could say that when I have maximum charge on the capacitor, I have 0 current through the inductor. So that's why we can get case 2, because if we have maximum charge in the capacitor, we have 0 current through the inductor. So one of the terms gets wiped out. And by symmetry, we could have also written the other extreme case where we had no charge on the capacitor because we had maximum current through the inductor. So realize this is very similar to a mass spring system, because you can find it by summing your spring energy and kinetic energy at any time. You could take your maximum spring energy, which relates to the maximum stretch, or you could take your maximum kinetic energy, which relates to max speed. So why are these mutually exclusive? Like, why can you not have any of the inner energy type when you're maximized? Well, if your capacitor, if you had current, if you had current in your circuit, your capacitor could still get more charge. And similarly, if your capacitor still had charge on it, some of it could discharge to add to the current. So we know that when one of those quantities is maximized, the other one is 0. So we see that we get 3 unique energy formulas consistent with our expectations. All right, so we're going to start with a numbers example. A 100 millihenry inductor and a charged 2 farad capacitor are connected to form a circuit at a certain moment in time. So this is any random moment that we're zooming in on. There's 10 to the minus 3 coulombs of charge on the capacitor and 4 times 10 to the minus 3 amps of current through the inductor. So let's find the energy stored in both fields at this time. So the energy stored in the electric field can be found by taking the square of the charge on the capacitor divided by double the capacitance. We had 10 to the minus 3 coulombs, and our capacitance was 2 farads, so lots of charge and lots of capacitance here. This one, we're going to cheat and look at my notes. This is 1.5. No, it's 2.5. This is 2.5 times 10 to the negative 7th joules. So that's how much energy is in the electric field. Then for the magnetic field, it's 1/2 times mv squared, because we said that this is sort of like a kinetic energy. So 1/2 times inductance times current. So 1/2 times the inductance, which was 100 millihenries, so 0.1 henries. And the current is 4 times 10 to the minus 3, and we square that. And if we do this one, we get 8 times 10 to the minus 7th joules. All right, so because it's going to be useful for later, we can also say that the total energy at all times for this circuit is a constant. And since we found the energies at one time, we actually know what the total energy is for all times. We might not know how they distribute, but we totally know, regardless of what's happening, the sum is going to be 10.5 times 10 to the minus 7th joules. Draw a quantitatively accurate bar chart for the circuit at this time. Well, let's see here. I think counting by, can we count by twos? Yeah, we can count by twos. So let's let's count by, let's say each of these ticks are going to be 2 times 10 to the minus 7th joules. And this is obviously 0. All right, so electric field. On the electric field, we're storing 2.5 times 10 to the minus 7th joules. So it is, so this is 2, and this is 3. So it's actually halfway. Of course, I'm using my best judgment. Sort of halfway between 2 and the halfway mark. So I'm going to put it just above 2, something like that. And this we said was 2.5 times 10 to the minus 7th. All right. Then for the energy stored in the magnetic field, that was exactly 8. So that is 4. That's 4 squares. Which makes it 8 times 10 to the minus 7th joules. And we see the total. The total would be somewhere up here. And that's a constant. All right, let's find the max charge on the capacitor, max current through the inductor, and the frequency of oscillations. So maximum charge, well, when you're at maximum charge, all of your energy is in the form of being stored in the electric field. So we can just set all of our stored energy equal to the energy stored in the electric field. So we could do some simple rearranging. So multiply everybody by 2c to get 2cu, and then take a square root. So Q max would be the square root of 2 times c times u total. And I'm not going to bother. Yeah, I will. Why not? Why not? 2 times 2 is the capacitance. Total energy was 10.5 times 10 to the minus 7th. And we better get a number that's bigger than the charge we started with. And my notes say that number is 2.05 times 10 to the minus 3 coulombs. So our initial charge, so we are all the way down here. And when barely any of our energy was stored in the electric field, we had just 10 to the minus 3 coulombs. So when we're fully charged, we have about 2 coulombs, which makes sense because doubling the charge is going to quadruple the field. Is going to quadruple the energy. So that gets us to 10. So it's just going to be a little bit above 4 times as much. And what about the inductor? Well, for the inductor, we do the same thing, right? U total is equal to 1/2 Li max squared. So slightly different rearranging this time, but we get I max is square root of 2 U total divided by L. So we get 2 times 10.5 times 10 to the minus 7th divided by our inductance, which was 0.1 henries. And that works out to something that is much, much closer to the original value. And we get 4.58 times 10 to the minus 3 amps. So if we look, we actually started with 4 times 10 to the minus 3 amps because most of our energy was already in the magnetic field. So we didn't have to have that much more current. And what's the frequency of oscillations? So people really confuse frequency and angular frequency. So the one we know is omega is 1 over square root LC. So what is that? Well, 1 over square root LC. L is 0.1. C is 2. We get 2.24 radians per second. So this does not tell you how many cycles you're completing. This tells you how many radians you're completing per second. So from that, you can either do a quick conversion, like you could actually do this with scientific, I forget what you call this. Chemistry uses this all the time. It's not quite dimensional analysis. It's just unit conversion, right? It's 2.24 radians per second. But I know that there are for every 1 cycle, there are 2 pi radians. So we see units of radians cancel. So we're left with 2.24 over 2 pi cycles per second, which is 0.356 cycles per second. And that actually has a very special unit that we call a hertz. So if you see Hz, Hz is measuring actual frequency, not angular. So be careful about that. And now we have a spicy example for our E&M finale. We have a two-phase circuit. So in the circuit shown below, the capacitor is initially uncharged. At t equals 0, we flip the switch to position 1 for a long, long time. So we put it in the LR circuit for a long time. And then we flip it over to make an LC circuit. So what do we got? First, we want to graph the current through the inductor as a function of time, letting downward be positive. So with these two switch questions, I always say, first thing, redraw it in each state. So what do we got? Well, first, in regime 1, it looks like it's an L over R circuit, so just that. And what's going to happen here? Well, we know that we initially start with 0 current because inductors say, oh no, you're not changing the current through me. So at time t equals 0, there's no current, but eventually we're going to get a steady state current of epsilon over R. So we can actually draw that now. And it says it's been a long time. So we can assume it has reached steady state. And then what about 2? Well, in case 2, we have now arrived at our LC circuit. And at this time, remember that inductors maintain currents. So there's an initial current of epsilon over R through the inductor at this time. And it's going to be an LC circuit. So it's going to start with current. That current is going to charge up the capacitor. The capacitor is going to discharge, flipping the current. Then the capacitor charges again, and so on. So we get a cycle. So this becomes an oscillator. So what I'm going to do here, did I guess correctly? Oh, I did. You are the dotted line. So trying my best to make it symmetric. And of course, this is just going to be some sort of oscillator. Something like that. So we see we get kind of this weird graph. Maybe I'm going to make it, I should make it touch. Oh, that's not bad. That's not bad. That's not the worst sine curve I could have drawn with no axes and no help. So we see that we get an oscillating current after that because there's no resistance in circuit 2. Now, a fun problem to consider would be what happens if there is resistance, which of course is much more realistic. You would get a damped oscillation, something like that. All right, derive expressions for everything. Approximate current through the inductor at t equals delta t. That's when we flip the switch. That's easy. We already know what it is. It's epsilon over R. Why? So we know that at long times, my inductor L is a wire gap. Nope, absolutely not. It is a wire, not a wire gap. So this means after a long time, I can literally replace my inductor with a wire. And this is just a simple Ohm's law. I is equal to epsilon over R. All right, maximum charge stored by the capacitor. So here's where we use energy conservation, because we just found what the max current is. Because as soon as I flip the switch, this is actually a case where all of the energy is stored in the magnetic field to begin. So we actually know that I max is epsilon over R. So we can start by saying the maximum energy I can store in the B field is equal to the maximum energy I can store in the E field. When is the B field maximized? When 1/2 Li squared is maximized. And then similarly, we get Q max squared over 2C for our electric field. And we see that 1/2s cancel, so we get Li squared is equal to Q squared over C. Then do some rearranging, and we get Q squared is equal to LC times I max. Oh, that's interesting. And then we take a square root, and we get Q max is equal to square root of LC times I max. Absolutely not a coincidence that this is omega, because you can actually use calculus to get this. Because if you did some trigonometry, you could relate the amplitudes like this. All right. Then we want the time required for the capacitor to become fully charged for the first time after the switch is closed. Okay, what does that even mean? Well, remember we have this sort of trading idea. So here, all of the energies in the inductor. Here, all of the energies in the capacitor. Here, all of the energies in the inductor, all the energies in the capacitor, all the energies in the inductor. So remember, these maxima and minima of sine and cosine happen quarter cycles apart, right? Maxima and minima occur every pi over 2. Because it goes pi over 2, pi, 3 pi over 2, 2 pi. So we see these are quarters. So we're interested in this time right here, which is a quarter period or a quarter cycle. So we can do that. So the time we want is, we want 1/4 of a cycle. So this is going to be equal to 1/4 of t, which is equal to 1/4 of square root LC times 2 pi. We derived this earlier, so I didn't rederive it. But if you want to remember how to do that, remember the period. We said the period is going to be equal to 2 pi divided by omega. Because omega is 2 pi divided by the period. So it's not 2 pi in front, it's a quarter of 2 pi in front, which is pi over 2. So that shouldn't be too surprising that there's a pi over 2 involved, because pi over 2, that's how often these maxima and minima are occurring in the cycle. And LC is our characteristic time. All right, and then last, a modification. Suppose we do the whole thing again, except instead of just a normal L and C, our new C has a dielectric inside. Describe how your graph of I of t will change once the switches move back to position 2. So obviously, who cares there's a dielectric here when it's in position 1, right? The circuit has no idea there's a dielectric here, so there's no change there. So what's going to happen? Well, this is our graph. So what does a dielectric do? So our fundamental thing that a dielectric does is dielectrics increase capacitance. So let's say that. So dielectric increase capacitance. All right, that's not a feature of the graph, capacitance. Oh, that's an awful spelling. Oh man. Dielectric. So we know that C goes up. Cool. So what does that do? Well, we note that the period is proportional to square root of LC. It's that, but a factor of 2 pi in front, right? So this means that the cycles take longer to complete. So by increasing capacitance, the curve gets stretched out. So think about literally stretching that sine curve over a bigger spot. And then lastly, we want to say whether the charge on the capacitor increases, decreases, or stays the same after we add the dielectric in. And you could reason through it conceptually, which might be a fun exercise, but I'm giving us the easier option. Just use your expression from part B. What does part B say? Maximum charge stored by the capacitor is this object. So we said that Q max equals square root LC times I max. So if capacitance increases, we see that our expression is increasing. So we see Q max is going to increase. So there we go. And again, I think it's fun to look at why this conceptually should make sense, that you're going to store more charge. You're going to store more charge on this capacitor when the dielectric is there. You can make some arguments about the weakening field, right? Dielectrics weaken the field, so you must have more charge in there if you're getting that same field strength between the plates. But yeah, that really combines a lot of things. We're back to simple harmonic motion. We got energy, electricity, magnetism, and that is where we end with LC. So the workbook is officially done.